Hello, welcome back to Piers Rocks. Today, I lay out a Raspberry Pi version of One ROM to replace 28-pin ROMs. The 24-pin version of One ROM replaces 2, 4 and 8 kilobyte ROMs in retro systems like this Commodore 64. In the last video, I implemented a completely autonomous ROM byte serving algorithm that doesn't use the RP2350 CPU at all, but uses the PIOs and DMA channels exclusively. And it performs so well that I expect it can replace some of the fastest 28-pin ROMs out there. In this video, I'm going to take this 24-pin RP2350 layout with a USB connector and extend it so that it can support 28-pin ROMs. In case you've not watched my previous videos about One ROM, I'll give you some background. The 24-pin version of One ROM is designed to fit in the same footprint as the original ROM socket. Here you can see One ROM next to an original 24-pin ROM. They're the same length. One ROM is a little bit wider, but no wider than the socket that this ROM installs into. I plan to keep the same footprint with the 28-pin ROM, just extend it by 2 pins at one end, which will give me an additional 4 pins, taking me up to a 28-pin ROM. The footprint made the layout of this 24-pin board extremely challenging. There's very little space to run all the traces involved. If you're interested in finding out how difficult it was, I'll link the original layout video in the description down below. This is a 2-layer PCB to keep the final cost of One ROM as low as possible, and I'm sticking to the same philosophy for the 28-pin ROM. I want it to be no larger than the original ROM socket for the 28-pin ROMs, and I'm sticking with a 2-layer PCB. There are a bunch of constraints on this layout, from the RP2350 itself, which has some quite strict requirements around how you lay out some of the supporting circuitry, but also from One ROM. The way that a parallel ROM like this works is it has a bunch of address pins that's used by the host system, like a Commodore 64, to indicate the address of the byte to serve to the ROM. It then has 8 data pins that are used to serve the byte, and it also has a number of chip select lines. Each of those 3 groups of pin types have to be kept contiguous in the final layout. Also, I want to take the opportunity to move to a USB-C connector on the 28-pin version of One ROM, as the PCB should have a little bit of additional space. What follows is the edited footage of me doing the most challenging PCB layout I've done to date, even more challenging than this 24-pin version of One ROM. You'll see the thought process that I'm going through as I'm going along, the mistakes that I make, and how I eventually get there in the end. And finally, just before the layout, if you're interested in getting an ICE version of One ROM, I just got hold of a bunch of additional stock. My online store is linked to down in the description. Enjoy the video. What you're looking at in front of you is the 24-pin USB One ROM Fire. The key difference with the new board is it's going to be 2 pins longer. Because in the 28-pin ROM, the pairs of pins down each side are the same pitch. They're 600 milliinches, 15 and some change millimeters. I don't get any additional width in the board to route traces through, and even though the board is getting longer, it's not going to be any easier to route because it's really the width that's restricted. The RP2350 takes a certain amount of width up of the board, and then the pins are at certain locations, so I only have that gap to route between them on both the top and also the bottom because of the way the power and ground traces need to be routed. That means I've got a choice, and it's quite an important choice of, do I extend the board by 2 pins at the top? Do I extend it by 2 pins at the bottom, or do I extend it by 1 pin in each direction? And I'm optimizing for a few things here. I really don't want to relay out most of the traces. I want most of them to stay where they are because, I mean, this took me an entire day to lay out this board, and I really don't want to spend more time than I have to on this next board. The other key change I want to make with this board is I want to move to a micro USB connector. I don't think this board, the 24-pin board, actually has enough physical space to fit a USB-C connector. It's possible I could do it with this Fire board by jigging a few components around, but I'm pretty confident that it's just not feasible on the One ROM ICE. So I think the 24-pin versions are going to have to stick with a micro USB connector. But if I can for the 28-pin ROM, I would love to move to USB-C as a more future-proof connector. That means fitting in a couple of extra resistors on the board, but with the additional length, assuming I can put them right next to the USB-C connector, that should be fine. The safe thing to do is to extend the board by 2 pins at the bottom. That gives me the maximum possible space down there for a USB-C connector. It would also actually allow me to move these boot and ground pads to a freer location on the board. Right now they sit under this flash chip, and that limits the size of the holes I can put through them. That in turn makes it more difficult to jumper these 2 pins together if I need to get the board into bootloader mode. So what's the downside of extending it by 2 pins at the bottom? I'm slightly worried that might give me challenges actually routing the traces I need to up to these pins up here. The chip select pins and the high address pins that are required on the 28 pin ROMs all sit in the top half of the board, so I do probably need some additional space for routing up here. So I think the way I'm going to start is I'm going to extend the board top by 1 pin and bottom by 1 pin. Hopefully that'll give me enough room on the bottom for USB-C, and it'll give me enough room on the top to route all the traces. I guess we'll see. It's not the end of the world if I have to come back and revisit this decision down the line, but I'd rather not to. Let's take a look at the difference between a 24-pin ROM and a 28-pin ROM. I built myself a nice visualizer, which is available on the One ROM website, for all of the different sorts of 24-pin and 28-pin, both mask programmable factory ROMs and EPROMs, all the way from 2704s up to the 27512. Which is the largest of the 28-pin ROMs. What we're looking at right now is a totally bog standard 2364. So this is used as a kernel and basic ROM in the bread bin Commodore 64. And you can see it's got, I think it's 13 address pins. Yeah, it goes from A0 to A12. And also it has a single chip select line, which on 2364 can be mask programmed low, active low, or active high. Now, the first 28-pin ROM, the smallest 28-pin ROM, is actually the 2764. So it's still an 8 kilobyte ROM, but it's an EPROM. And they went to a 28-pin form factor for this. You can see we still go from A0 up to A12, but notice that A12 has moved over here. And on the 27 series chips, all of the 27 series chips have 2 chip select lines. They have chip enable and they have output enable. And these are both active low, and they both need to be active low for the ROM to serve. There's also some programming pins on these, which we don't really need to worry about, although users of One ROM need to make sure they don't insert a programming voltage like 20 volts into One ROM, or that would definitely kill the chip. All of the 27 series ROMs are pretty similar. So if 2764 is this, we look at the 27128 and we have an extra address pin, and some of the programming pins move around as well. But output enable and chip enable stay in the same place. There's the 27256. Here we have an A14, and then we go to the 27512 and we have an A15. Actually, I misspoke earlier when I said that there's 2 chip select lines on all of the 27 series ROMs. This one, the 27512, is 64 kilobyte ROM, only has chip enable as active low, because this is being used as a programming pin 22. But it's pretty similar. Now, why are we looking at this? Well, remember, all of my address lines have to be contiguous, a contiguous block on the RP2350, so that whatever ROM byte serving algorithm we're using, whether it's a CPU one or a PIO based one, works. And all of the chip select lines need to be contiguous as well. Well, that's pretty easy if there's one chip select line. And all of the other 27 series ROMs have the output enable and chip enable in the same locations. So again, that's pretty straightforward to achieve. However, the 23 series ROMs are a little bit different. So the first 28-pin 23 series ROM is the 23128. So what's that? That's 16 kilobytes. And this is used in the later Commodore 64s as a combined kernel basic. It's used in a later 15412 disk drive, and this is used in a Spectrum, for example. So this is quite an important chip to be emulating. Now, we can see that address 12 is in the same location as on the 27128. Great. We can see we've got chip select lines as pin 20 and 22. Okay, they're factory configurable. That's easy for me to deal with in the One ROM firmware. But chip select 3 is also present on the 23128, and it's on pin 27. So I have to make sure that 20, 22 and 27 of the ROM are contiguous when they get mapped into the RP2350. We'll just have a look at the 23256. This one's straightforward. It's got 2 chip select lines in the normal location for other 28-pin ROMs, and I'm pretty sure the address pins are in the same location as the 27256. They are. And then the 23 5112 is again pretty straightforward. Everything's in the same location as the 27512, but we have two chip select lines here. So again, really what I need to be focusing on is external pins 20, 22 and 27 of One ROM need to be mapped as contiguous pins on the RP2350. I'm looking at the schematic now and trying to figure out what's got to change. CS1 here, that is going to have to move to be probably, it's either going to have to be between the data pins and the address pins, or it's going to have to be completely at the top of the GPIO space, sort of pins 24, 25, so that the address pins themselves stay contiguous. Now I'm coming to look at the physical board here. This dot on the chip is pin 1. There's 15 pins on each side. So over here we have sort of pins 31 through, I don't know, 46. 31 through 37. That would put my chip select lines down here if I leave them in the current location. I really don't want my chip select lines over there. That's going to be a massive pain to route them. They need to come to this side of the board. So I think actually I'm going to need to put my chip select lines between the data pins and between the address pins. So GPIOs 8 and 9. So pin 12 and 13, they're in that location. That's an ideal location to be going up to pin 27 up here somewhere, and also to pins 20 and 22 over here. So yeah, the chip select lines are going to have to go between the data lines and the address lines. So I'm going to need to move A11 and A10. And I'm going to put chip select 1 here. Now, I just need to think to myself, what is chip select 1 actually going to map to? Well, on the external ROM socket, that's pin 20. So I'm going to call that chip enable. I'm also going to want, I'm just going to create a new pin type. Okay, so I've got output enable. That's going to want to be next to chip enable, because I'm always going to want to use chip enable and output enable. Now, in some cases, the 23128 chip, I'm also going to want to have chip select line 3 here. And so that I'm going to create here and put it contiguous with OE. So this is CS3, and I'm not going to put the inverted symbol on it because it could be active high, it could be active low. CS3 is also A14. This is my best guess of pin assignments, given not having actually tried laying anything out at the moment. So GPIO 15 is on the right hand side of the board, and GPIO 16 onwards on the left hand side of the board. So I've tried to assign the address lines and CS lines to be compatible with that, and I may or may not have got them in the right order. I won't have got them in precisely the right order to lay this out easily. I think the data lines can stay as they are. I've had to get rid of the X pins because I'm just not going to be able to support them on this ROM. At least I can't figure out a way of doing that. I've got these two cell pins. Now, actually, these might be able to be used as X pins for various purposes in future, as well as being image select jumpers. I only have... No, they won't be able to be used as X pins because these pins here are not 5V tolerant. None of the pins that support ADC function are 5V tolerant on the RP2350, at least the RP2350A. So these are only going to be able to be used for select pins, image select pins, the V-bus detection, so we can detect when USB is plugged in, and also control the LED. So that's what those pins are used for. So I'm using all of my 26-pin 5V tolerant GPIOs, and I'm also using the 4 non-5V tolerant GPIOs. The other change I need to make to the schematic is I need to replace the USB-B micro connector with a USB-C connector, and I need to add in a couple of 5.1K resistors to ensure that USB-C is negotiating 5 volts for this board. Thought we'd digress a little bit and go and choose a USB-C connector together. So this is the JLC PCB parts list. This is very similar to LCSC's website if you buy parts from LCSC. In fact, LCSC are just JLC's parts arms, but you want to look at the JLC's parts library so you can see how many parts they've got in stock and which are basic parts versus which are extended parts, because you'll pay more to have boards fabbed with extended parts. So I'll go and find USB connectors. I find that the search function doesn't work terribly well on this, so I tend to go and drill down on a particular connector type. That then takes us here. We've got 6,915 parts. That's not very useful. So first of all, let's enable economic PCB assembly. Well, okay, that's taking me down to 6,500. That's not terribly useful. Let's search by or filter by the amount of stock they've got. So the USB connector they have most of, they have 683,000 USB Type-C connectors. That looks like what I want. Now, what I need to be sure of, though, is there are USB connectors that do power only, and there are USB connectors that do data and power. I need a data and power one. Now, immediately looking at this and seeing a 16 pin, I'm pretty confident this is going to be a data and power connector. And if we look down at the easy EDA diagram that JLC expose, we can see we have DP1, DN1, DP2 and DN2. So that's D plus, D minus, both 1 and 2 variants, which you have because you have one on the top and one on the bottom, so the USB-C can be connected in either way around. I'm just going to tie those together in my schematic. DP1 and DP2 will be connected together, and DN1 and DN2 will be connected together. That's the easiest thing to do. It needs the fewest parts. Obviously, we have VBus. We need VBus. That's about all we need. I suspect CC pins are for the resistors that I need to add into the design so that 5 volts is negotiated via the USB-C connector. And we can see that in a quantity of 1, this is going to cost me 6 cents. It's pretty good. Now this is, and I'm sure this is an extended part. Yes, this is an extended part. I actually noticed when we were here looking at all the USB-C connectors, there were no basic USB-C connectors at all. So we have to pay for an extended part here. This costs $3 per assembly order. So if I order 100 boards of this design to be assembled from JLC, they'll charge me $3 extra for this part, plus 6 cents per part. So if you're buying a lot of boards, then the $3 becomes negligible very, very quickly. Now, I'm not going to be ordering 100 boards. I'm going to be ordering 5, the minimum, for prototype purposes here. But I want USB-C. Well, I want USB. What am I going to do? I need to use an extended part. It's the way it is. Other things I just want to take a quick look at is PCB assembly type, economic and standard. Well, I'm going to use economic because that means cheap. And they support that, so that's great. And it's a surface mount component. Even though it's got pins, which will go into holes on the circuit board, so I will choose or have to design a footprint with holes here in these locations, it's still considered a surface mount part. I think what JLC do is they will essentially paste over the holes and then position the part on top, and then when it's reflowed, that solder will wick down into the holes and keep the pins in place. So this looks like the part I want. I'm just going to go back to the parts list and have a look at the other parts. I'll spend a bit of time looking at the various USB-C options here, and the top one is the one I want. 16 pin, it's only rated to 5 volts. All I need is 5 volts. So now it's time to add the part into my schematic. So I want a 16 pin USB-C. So VBus, CC1, CC2, D minus, D plus, S bus, ground, shield. That looks correct to me. So let's whack this on the schematic. Oh, it's much bigger, isn't it? Let's put it down here for now. Next thing I'm going to do is I'm going to see if there's a footprint already associated with this USB-C connector. So I've printed out the drawing of the USB-C connector that I plan to use, and I'm trying to find a match for this in KiCad's existing footprint library because I don't really want to have to draw my own. And this is very, very close. I need to stare at it in detail because it's not precisely the same. I'll go through and I'll check the dimensions and make sure that this part that I've selected from JLC is actually a good match for this footprint. I've had a good stare at the technical drawing and measured all of the dimensions on this footprint. And there's one difference, and that's that these two holes, S1 and S12, the bottom two holes here, the Y dimension of these holes was 1.2 millimeters inside and 1.6 millimeters outside, and the technical drawing says there should be 1.4 and 1.8. So I've changed those values over here. I'm going to save this off as my own footprint and mark it as a footprint for the LCSC part number that I'm using here. I suspect that the part I'm using is probably a clone of the part that this footprint was originally designed for. And I don't know if this was an inaccuracy in the original footprint, or these guys have got a slightly different dimensions on it, or they've decided for slightly different size holes, maybe larger holes for more solder to hold the legs more securely. I don't know, but I'm going with the technical drawing for the part that I'm actually using. One other thing to say, there's a courtyard around this, right? Courtyard means don't put any components in there. I can play pretty fast and loose with this courtyard because it's not something that the manufacturer specifies. And the legs that go into these holes are on the outer side of the component. So if I look at the drawing here, I can see that the legs go right up to each side of the component. I can actually go in this courtyard if I need to. So that's something that's quite useful to be aware of. So I've got the USB connector in my schematic now, and I want to make sure that I actually select the footprint that I've just modified. So that needs to come from my footprint library. It's that one there. So that's now the right part number for LCSC. So this will get generated as part of the BOM, and JLC will choose the right part. That's the right footprint, so it'll give me the right land pattern for this on the PCB itself. So that's much of the work actually done. It's always a bit tedious and painful selecting a new component to work with. Now, when I use USB-C connectors on any of the boards I do, this is the first time I've used USB-C, assuming this board comes out well, this is the schematic symbol and the footprint that I'll use for all of my designs. So I've got my USB schematic now completed, I think. So I've got VBus connected on my connector, and that's also connected into my electrostatic discharge diodes. I've got D- on the top and bottom of the connector tied together, and D+ on the top and bottom tied together. I've got CC1 and CC2 both tied to ground through 5K1 resistors. That should give me 5 volts up to 3 amps. I've not got connected the sidebar 1 and 2, and I've tied the shield to ground. Everything else I think stays the same here. I still want my Schottky diodes to stop either 5-volt source back feeding the other 5-volt source. And I've still got VBus connected into my RP2350 through a resistive divider. And that partly provides a little bit of... Well, partly it's because I'm using an ADC pin, so it can't take the full 5 volts. And partly it provides a bit of additional protection against an electrostatic event. Now, someone said in the previous video, I think when I was laying out the original RP2350 USB board, that Raspberry Pi don't specify using ESD diodes. Okay, fine. I'm still going to include them. This particular room that I work in during the winter, when it's nice and warm and toasty, the carpet generates huge amounts of electrostatic, and I don't want to be zapping my boards. All the data pins are connected, all the address pins are connected. Note that A14 is CS3 on the 23.128 ROM, and I've got CE and OE connected, so this should be good. I'll run the electrical rules checker, make sure everything's okay, and then we'll move on to the PCB. Yeah, I still got some problems to sort out. Cell C, Cell D, CX1, CX2 are no longer used, so I'm just going to delete those from the schematic. For now, I'm going to leave the 2x4 pin header. I may well collapse this down to a 2x2 pin header in the future. We'll see. Now, I've updated the schematic. I've updated the footprint assignment, so I can bring those new footprint assignments into the design. I'm not going to delete anything. I'm just going to bring in the new stuff. So I've got 4 things. I've got the USB-C connector. I've got the 2 new resistors. We'll just get those out of the way because they're in the way a little bit. And then we have the new pins that we'll need to replace the old pins. So I'll lay them over the top, get them exactly where I want them, and then I'll delete the old ones. But this way I can make sure they end up in exactly the right place so that I need to move as few other things as possible. Now just remember that right now I've got a 2x4 header here for the image select pins. And I've got this component here which I don't think is needed. I'm going to move this out of the way because I suspect this is just going to get deleted. This we might be collapsing down to a 2x2. Now this is actually quite exciting to me because I might have enough room to expose an explicit SWD serial wide debug connector on this board, and if I can, I will. The SWD pins from memory pads are sort of around this location. If we look at the underside, yeah, we've got SWDO and SWClock here, so it might be feasible to get those up to here. No promises, because I would have to get across all of these traces. I don't know that it's going to be possible. I don't know that it's going to be feasible, but if it is, we'll get it done. So I've decided to give myself the extra length on this board at the bottom. And the reason I've done that is look at the size of the USB-C connector compared to the micro USB connector. It's essentially an extra pin longer, you know, one of these longer. So that's about 2.54 millimeters, because that's the pin pitch of these pins here. And it's wider as well. So if I only give myself one extra pin space at the bottom, then this micro USB connector is going to eat up all of the spare space. And I'm not going to be able to fit components to the side of it like I do today. So I need all this space at the bottom. And that's okay, because at the top, I no longer use these X pins. They're gone. And this 2x4 header is going to become a 2x2 header. So it actually gives me oodles of space up here. I may even be able to get SWD pins physically broken out to proper pins, and or boot 0, the boot cell pin on the RP2350 broken out on this board. I'm quite excited about that. So this USB-C connector is going to go down here. It's going to go in the middle here somewhere. And then this is the space I've got up here, essentially. So this gives you an idea at this point of what it's going to look like with the USB-C connector. The USB-C connector is massive compared to everything else on the board, isn't it? I guess it's about the same height as a micro USB, maybe slightly taller. But it's so much deeper, and there's just more volume to it. So the next thing I've got to decide is whether I sneak components next to it or whether I put them slightly higher up. I really like the fact that the status LED at the moment is on the edge of the board, but I think in all conscience I can't put it either that close to the USB connector or really that close to the pads. Actually, the pads, there are other components that are just as close to the pads, so maybe I can get away with that. I don't like that, and I think JLC might object if I do this. They just might object that they're too close. So I think I'm going to have to move the LED up to here somewhere, and I might just put it right in the middle of the board, just above the USB connector here. Now, I'm not out of the woods yet, because I haven't done any routing of the USB traces. I don't know how complex that's going to end up being, but there are more traces here. I'm going to have to put in these new 5.1K resistors. Now, resistors are going to be fine to go down the side here because they're narrower than this LED. This is an 0603 LED. I'm using a basic part from JLC's list for the LED. That's why it's red. It's the only 0603 basic LED they've got. Otherwise, I'd use another colour. I could go down to an 0402, but that's going to be more expensive because that will be an extended part. There are no basic 0402 resistors, LEDs. So I could go down smaller. I'm not going to do that. I think this Schottky diode, though, I think that's going to be okay to be right down here between this pad and the USB-C connector. I don't think JLC will object to that, but the worst they can do is tell me no and I have to come and lay it out. So I think I'm going to put the Schottky down here on the side. I'm going to put some resistors. Maybe I'll put the Schottky down here. I'll put the resistors down here. Now the Schottky needs to be close to the electrostatic diode, and that's definitely not going to fit down here. One of these resistors is the resistor for the LED anyway, so maybe I'm going to stick some resistors down the side here, get them out of the way. Maybe leave this Schottky here and this electrostatic diode here, and then I've got some space for routing traces here. That's what's currently in my head. Remember, there's a lot more to do. I've got to reroute a whole bunch of traces from the RP2350 to these pins over here. But, you know, first job is done. I've got the USB-C connector where I want it, and it's basically perfectly in line with the edge of the board. And you can't necessarily trust the 3D model on this, but I've checked the dimensions against the technical drawing, and I'm pretty confident that, you know, plus or minus a fraction of a millimetre, this is going to be pretty much on the edge of the board. That's how I want it. So I'm going to continue by laying out the USB on this board. Probably won't be the final layout, but I just want to get everything connected and working. When I'm doing a circuit board design, I like to get to a point where everything is connected and the design rules are passing as early as possible. That then tells me I've done the hard bit. I can now concentrate on making it aesthetically how I want it to be. So first step, I'll get the USB laid out, then I can move on to looking at connecting the CS lines and address lines back up. So immediately annoying to me is the fact that the CC1 and CC2 pins are at different sides of the connector of the PCB. I want both of the resistors. I want to tuck them down in here, get them out of the way. So here's the plan. This Schottky diode and the electrostatic diodes, I'm actually going to move both of them and put them here instead, at least for now, as I'm so fond of clarifying. The 5 volts probably isn't going to want to go around there. It's probably going to want to go all the way down here. So I'm just going to put that in temporarily. Okay. Now, I might be able to sneak it through. If I can sneak it through, that's fine. But remember, there'll be more traces coming down here. They'll either be on the top side or the bottom side. We'll see what happens. I need to get VBus fed in to the Schottky diode and to the electrostatic discharge diodes. So I'm going to take that. Well, I was going to take it here. Let's see if I can get a larger trace. Remember, this is going to power the PCB in some circumstances. So I at least want a 12mm trace. I can get a 12mm trace in. I'm just checking I've got enough space between this non-plated through hole. Looks like I've got maybe 10 mils. So that's probably okay. So I can bring VBus round like that. That's quite important because I want to take all the other traces out the top side of the connector. I'm also going to want VBus to come out here to go into the resistive divider. Now, I got a choice actually whether I do that directly from here or whether I go via the electrostatic discharge diode, which is probably a safer thing to do, because then if there is a, several thousand volt shock gets put into this board, it will have to go via the electrostatic diodes before it gets to the resistive divider, before it gets to the RP2350. I don't know if that's an electrically sound conclusion to reach. It sounds logical to me, but what do I know? I'm a software guy. So I'm just going to connect VBus up to the electrostatic diodes. Actually, I'm going to move the diodes up. You'll see why in a second. So I'm going to put those there. Then I connect VBus in like that. Then I can bring, and I only want a small trace, or it only needs to be a small trace that goes to the resistive divider because it's not going to be powering anything, and KiCad won't let me take a small trace from that side, so I'll bring it in from this side. Right? So that's now VBus is all connected. But I have a problem, right? Because I have to get that, which is that pin, into there. Let's connect D plus first. I'm going to connect the two D pluses together like this on the back side of the connector. And then I can go up like that. But I'm probably going to have to use a veer if I want to take VBus in this direction. Let's just stick a veer in. Ooh, I don't know. Let's put it there. Right. And get rid of that trace. I don't know what happened to my trace. It just sort of disappeared. So let's connect that up. Right. So now, can I get D minus around there? Yes. Okay. So that works. It's not like necessarily a good design, but it'll do till I have something better. Right, that's a bit better. Right, okay. So then I've got D plus D minus from the connector. And D plus and D minus. What am I doing? I'm thinking that I wouldn't have ground closed off like this if I swap D plus and D minus around. Actually, that's irrelevant. I'm thinking that the ground wouldn't be enclosed like this if I could take D minus up this way, which actually would mean turning this into D plus and taking it up this way, because D minus is over here, D plus is there. Although there is a one-time programming option on the RP2350 I've discovered, which allows you to switch the pins that D plus and D minus are used for. I thought this was fantastic for people who screwed up their PCB layout and connected D plus and D minus the wrong way around. You can just go into your RP2350, if you can get it into boot cell mode and somehow connect to it, you can one-time program it, and hey presto, you've just switched the way that the RP2350's USB support is working. So fabulous. Anyway, I'm sort of optimizing at this stage. I don't need to optimize. So let's just connect that over there, and that gives me room for a veer. I don't know though. I'm going to use this layout, but it looks all right. Now, remember, I want my little resistors, my 5.1k resistors sitting over here to be down here. So I'm going to have to get that trace and that trace across VBus. That's fine. I can drop them through the board with vias and connect it. And are my grounds going to connect? Well, they should do, really, shouldn't they? Yes, fine, brilliant. Ground's connected. Resistor's connected. That's my USB wired up at this point. I can get rid of the micro USB connector. Don't need that anymore. Gets rid of my air wires. Let's reconnect the LED. I really want it in the middle of the circuit board, which would be... I can find the middle here. This pad is in the middle. Middle must be there. Right. It doesn't want me to put it there because of the electrostatic diodes. So that's a pain. So I'm going to stick it here for now. Don't want it to go here. Fine. I'll come back and fix it later. So let's connect up to... See, previously this LED was going around here under the board. It can go here instead. And I can get rid of this. Gone. There's an air wire there. Why is there an air wire? V-bus. Oh, there's two V-buses. Didn't realise there were two V-buses. That looks ugly. But it'll do for now. Right, yeah, I'm good with that. My USB is all connected. It's not going to be pretty. That LED is not in the centre of the board. That LED has to be in the centre of the board. And I have to do that. Yeah, let's fix that. Now, the reason why I'm fixing this now, because it's an optimization, is because I just thought of how to do it. And if I don't do it now, I'm going to forget how to do it. And the way to do it is to rotate this diode 90 degrees, and then I can shift the electrostatic diodes over. And I know there'll be people saying, look, Piers, you're just wasting your time. Well, my time to waste. That's in the centre of the board. That's what I like to see. It's going to be functional at this stage. I haven't run a design rules check. I expect it'll be fine. If it's not, come and fix it. Anything that's wrong here, I can fix. So now I'm going to start laying out the other traces, the address pins and the CS pins that have changed their pin mapping. In terms of the address and data lines, I'm going to just start rearranging them. Because I pushed the pins down to, that's where the extra length went, all the pins at the bottom of the ROM will have to, all the traces will have to move down 2 pins, because all of the sort of bottom pins on the 28-pin ROMs are in the same location as the 28-pin ROMs relatively, so they're all at the bottom pins. So you see D3 here actually is now down the bottom. That used to be D3 there, so I'm going to have to move everything down. Should have enough space to do that, but let's see. Now these pins down here, D2 wants to come all the way down to there. D1 comes down to here. Just going to need to shift everything over a little bit, leave enough room for D2. Or A0, no, D0. So D0, is there enough room now? Well, there isn't if it uses a massive trace. Yeah, there's enough room there. There we go. Now, to get to A0 is, if it's up here. Right, yes. Okay, so this is going to be a challenge, because I need to get another trace down here, and I don't think there's enough room. Let's have a look. Basically, no, because I can't put it any closer to the edge than that. So that's a problem. It's probably a solvable problem, but it's a problem nonetheless at the moment. I also have to get A1 to A1. So this is all problematic. This is all definitely problematic. This is going to need a bit of staring at and musing on to figure out how to rejig everything, because that V-bus det has to get down to this resistor. Those cell pins have to stay there because they have to be after the GPIO pins. The GPIO pins have to be further up, but I'm still going to have to get, so the address pins are going to have to be higher up, and the data pins are going to come from the other side of the board. So somehow I've got to get the address pins from above these 2 resistors down the side here. And I've got some more, what are they, resistors, capacitors down here. So I may need to take these components and sort of shuffle them across this way. And I do need to be cognizant of the fact that this is all the VREF circuitry. I think that's just a regular decoupling capacitor. So I need to be careful about how I do this. If I can move this decoupling capacitor maybe round here and have quite a long trace through it, it's not ideal, but it gives me a lot more space to run traces through if I can do that. Anyway, I'll stare at it and muse on it a bit. I came to a realization while eating my dinner. The first thing is, the challenge I'm facing here is as a direct result of deciding to put the pins, 2 pins down from where they were before. That means I've got to get more traces down here. So this is going to be the most challenging part of the layout, I suspect. The other realization, which you'd probably already noticed, was I'd previously had these pins as select pins and they went through the board with vias. So I can still drop these pins through the board with vias and use that to access these pins down here. So what I think I'll do is I'll do a slight reordering so that this pin here, pin 37, goes to A0. Pin 36 goes to A1, and so on, just to make it a bit easier to route the pins. I'm also on the underside of the board going to need to shuffle these bits of traces over to the right here to then make sure the vias drop through the board to the left of them. Then I think it's going to be relatively straightforward to route these traces. So that's the plan. So I've rejigged these traces around a little bit underneath in the hope that I can break out the vias over on this side, on the left hand side of these traces. I'm pretty sure I can now, but actually I'd like a bit more space down here. So I want this V-bus det, I really want to come to the right hand side of A1. And we looked at this before, and LED 0 and 3.3 volts are in the way. Think I can get around this by taking this decoupling capacitor and pushing it down and rotating it. So rotating it will allow me to connect the ground up to this ground and onto that ground. And then I'll start to bring the 3.3 volts around this side. But I'm hoping, because the cap is a bit further down here, there'll be room, because these circles go in a little bit. May not be. A little bit worried there may not be. The other thing I could do is I could move this inductor. I could just shift it right a little bit. I want to be quite careful with this bit of the circuit because this is all to do with VREF, which is very, very sensitive according to the documentation. But if I shifted this over, then I could shift these caps over. I think this is a cap and that's a cap. And that's a resistor. I could shift those up a little bit and then I still have room for this ground to get around here. So I think I'm going to do that. I'm going to move this over a little bit. Right, I think that's a good connection. It's no different really to how it was before, but there's now a greater gap here. So I think I can reasonably push these over a fraction of a millimeter. Oh, actually, I don't think I can move this trace over, having done all that. But I can move this cap over, and then I still got a path for the ground. Take this, rotate it, put it next to the other. Actually, I think it's a resistor, that one, not a capacitor. It's nice and close. And then this all just feels a little bit more efficient. 3.3 volts. Now I can move that to there. That, I'll connect that with a fatter trace. Goes into that ground, and that goes on to the via over there. I could actually get a ground in there, I think. So some of these components use custom Raspberry Pi footprints, so you can fit traces between them. So for example, a footprint's used for this, so you can get this trace between them. So if they can do it, I can do it. So really now I just need to persuade KiCad to let me do a thin trace. So that looks, I don't need this bit of it. So now I have the ground connected in multiple locations. So that's excellent. This component here, off camera, I actually rotated it so that V-bus det could just come down here instead of going across. because this ground used to connect over here. I'm going to have to somehow connect it over here. I don't think that's a big deal. I think that's going to be relatively straightforward to do, although I haven't figured out how to do it yet. I'm sure I will. I can shift this LED trace over, and then VBus det fits between them, just like that. So that, and actually does a ton of extra, well, a ton of extra space. There's a very small fraction of a millimeter extra space. So what am I trying to do on the top side of the board now? What I'm trying to do is get A0 down to A0. So pin 37 needs to become A0. Pin 36 is probably A1. Pin 35 is A2. What about A3 and A4? Yeah, I want to swap A3 and A4 around as well. So A0 through to 7 in that order is probably good. Just a reminder, it doesn't really matter what the layout is of the address pins, so long as they're contiguous next to each other, because I can just define a new pin mapping config file for this particular hardware revision. That's like a 2-minute job. I need to reload. So A0 is there now. How am I going to get it down? I don't know. More work required. So I have some somewhat immovable constraints. This pad itself isn't immovable. I don't really need a pad there. I don't need a 3.3 volt pad there at all if I don't want one. But I do need to bring 3.3 volts down through a via to this pin, because I need to get 3.3 volts to here. I say I need to. Actually, strictly I don't need to, because 3.3 volts is being routed around the entire chip perimeter underneath on the top layer. But I really want to keep 3.3 volts there if I can, so that I get the maximum possible trace widths to everywhere that's drawing power. So if I consider that an immovable constraint for now, I have to have this trace. It can be thinner, but I still need to have the trace. Even if I made this trace 6mm, I don't think I'd be able to get another trace through there. So that's a problem. These vias, I can't move the 3.3 volt trace because these vias are in the way, and I can't move the vias because there's traces that are being broken out from the RP2350. I could potentially move these up, and that would give me a bit more space to drop vias through closer to the RP2350. But that would then stop me dropping these through vias, which I'm going to have to do. I could potentially take one of these two cell pins, or traces. I could potentially take one of these two cell traces and have it drop down through the board, maybe there, and then bring it back up this way. But that's going to be problematic because I'm going to have to bring traces back up through the board for these address pins in that location. So that's not great. So I'm beginning to question if this can be done, at least with the constraints I've imposed upon myself. Maybe I have to accept that 3.3 volt trace cannot be. I could potentially take these cell lines up the other side of 3.3 volts. Allow me to... How would that help? And then I could bring 3.3 volts over here, but this is an immovable constraint. This is something I simply can't move. This 1.1 volt line has to come from here, and it has to go to the bypass cap here. Right, I do have a plan. This 3.3 volts here, I'm going to actually pull it out here instead and take the cell pins round the other side, if I can, by moving this address pin over. That then allows me to bring the 3.3 volts up this way. And then basically saves me from having to have a trace to the left of cell B, so I can get at least one trace through here. So I'm going to do that now. I've made room for one trace now through here. So the 3.3 volts comes up through, and I've actually dropped a via through underneath the RP2350 on the 3.3 volt line. Previously the via was over here. That allowed me to shuffle everything around a bit. So I can now get a trace through here. So A0 can be routed. So I'm going to route A0. Although now I've just noticed that ground comes out here. I think that's fine because I think ground's connected over this side of those components. So I really just want to drop this through the board. That's a massive via. Smaller via. And now I can get it to A0. So A0 is now connected. A1 is not. A2 is not. And I'm going to have to get both A1 and A2 past these components here. One's not too hard because one of them can go around the outside like A2 is going at the moment. But they can't both do that. So let's take A1 round there, and then I only need to get A2 to there. This might work. So I need to move these traces down here. Get this bad boy over there. And then A1 I'm taking around the outside. But I'm going to have to get A2 across it. Well, I'll tackle that in a moment. Right, A1 is connected. Hurrah. I wonder if I can drop A1 through a via just here. Going to give that a go. Yes, I can. Just. If I move that, I've got a bit more space. I want A2 as a via. That's fine. That's good. I can make that work, I think. So A1's connected. Excellent. Yes, A2 I can now drop through. I remember what I was trying to do. I was trying to move everything sideways so that A2 has room to come round pin A0 round this way. So let's keep going. Get these traces shifted over a bit. They can't really move any more in that direction now, as far as they'll go. So yeah, I want A0 to move over, so everything's going to have to move over. Okay, A2 moves, A1 moves, A0 moves. That gives me enough room, I'm fairly sure. So A2 comes through here. Hooray! Excellent. So now, how is everything looking? Well, ground is stitched through the board, so that's fine. Let's put another stitch through there as well. So I feel like I've achieved the impossible now. Why is everything A4? I feel like one of those films. Oh yeah, the Matrix with Matrix 2 with whatever the rogue agent was called, and everyone turned into the rogue agent. Everything's turned into the A4 trace. It's A3. How are we going to get A3 to here? Can you say via? There's room for a via. And this isn't pretty right now. I'm not sure it's going to get that pretty. But I've connected A4. A3 and A4 are now connected. So why does A3 want to connect to A3? That's because that's not A3 anymore. That's A6. Now, A5's there. A6 is above it. I want this to be A6. This lower pin. So it can come around the outside. And I want this one to be A5. Right, that's done. So now A5 connects to A5. A6 connects to A6. What about A7? That's already connected. That's not moved. That's always been there. So it's still connected. A12 is not connected properly. It's connected to something else. And A15 won't be connected properly either. Where do they actually go to? A7 and A12. A7 is connected to A7. A12. Awesome. A7, A12, and A15 already connected to the right place. So the next challenge is going to be to route all this stuff again properly. But again, I'm going to have to reallocate the pins to make the routing easier. But I think pretty much everything's done on this side of the board. I think I've done the bottom, the USB connector. I've done the pins down the bottom. I've done the pins on the left-hand side. So now I only have the pins on the right-hand side to do. I think the biggest challenge on this side of the board are going to be the CE and OE pins, and possibly also CS3, which is A14, because those have to come from a contiguous set of pins on the RP2350, and they have to be between the data pins and the address pins, or they could be before the data pins, but that's not going to work because I'm not going to be able to reroute everything, or it could be after the address pins, and that's not going to work because they'll be down on the wrong side of the board. Those are the pins I'm going to try and route first. the CE, the OE, and the CS3 or A14 pin. Then once I've got those routed, I'll figure out what the allocation needs to look like of all of the other pins. One thing that helps me here is this all looks very tight, this location. But this is going to be okay. I have space above these components to move these components up if I want to do that, and leave more space around here for my address lines and CS lines to come out and drop through vias and route to the appropriate location. So while I'm not actually changing this bit of the layout right now, I strongly suspect this bit of the layout is going to change and become a lot easier. So I've just routed this 5-volt line up around here instead of coming across here. Just now takes it further up the board and more out of my way. I can actually get it even higher up the board and more out of my way, which I'm going to do because it'll make it easier to get hold of this pin here by taking the vhost line and bringing it up round ground here. Now that disconnects this ground from this ground on the top side of the board. That's fine because they're connected on the bottom side of the board. Then I can bring this 5 volts here round and down this way. So I've made a bunch of room for myself. Again, this component here, I suspect this component here is going to move up to here fairly soon, highly likely. And now is also as good a time as any to sort out the 5-volt line down here. I might as well just take it straight through there, and I have no trace around there now. So I think that looks a lot better. So now I need to actually figure out how am I going to get CE, OE, and this line here. Just remember, CE and OE have to be next to each other, and CS3 has to be next to them. It doesn't necessarily matter what order they're in, so long as CE and OE are next to each other. There's another constraint that this C3 pin also has to be next to the address pins, because it's sometimes an address pin. And I'm pretty sure I've got that set up at the moment, but I'm going to double check. You see, CS3 is the last one. It has to be physical pin 14. I cannot move that, but I can swap CE and OE around if I want to. With that in my kit bag, CE. It's that pin. Oh, it's quite a long way, isn't it? OE. Oh, that's quite a long way as well. My immediate reaction is this isn't doable, because I'm already using up basically all of the board to get the data lines from here. The CE and OE line have to be up here. Can I get them through the board? Well, here's one thing I can do. I can move this ground over to here. I found a way of making another trace available. This D5 comes down to the right of D4. It could come round to the left of D4, and then it would need to be D3. Right, again, it's not pretty, but it's routed. I give myself a little bit more space if I move this component down. I don't have space because this 3.3 volts has to leave a gap. I can potentially rejig all the components here, but I don't really want to because there's a lot of traces and it was a bit finicky getting it laid out in the first place. But I think the next step is I need to route D6 down here. Anyway, so let's break D6 out somewhere. Pop it into a via. I don't know how I'm going to get CE across it or D7. Oh, it's a nightmare. It's an absolute nightmare. I'm just not at all sure this can be done. I don't see how this can be done, because these pins here, data pins, basically have to break out here, and together the vias and the tracks use all of the space available on the underside of the board. I've then got other data pins up here, and remember the data pins have to be down here. I don't think it's possible to put them anywhere else on the chip. I mean, down here these are all not, there's no GPIOs down here at all, and these are the non 5-volt tolerant ones. So I have to use these, or I have to use these and take them across the board this way, and I can't see why that would help me any more. And CE and A10 are south of this bypass cap here. I have to get both of these two traces to this side of the board, and I don't think it can be done. There's no room. These vias, I can shuffle them very slightly that way maybe, but not a lot. If I can shuffle them over, I can get maybe A10 up. I don't see how C10 is going to go. Sorry, CE is going to go. And CE has to get up to there. CE, OE, and CS3. I think those are probably the best locations they could be in, given the constraints that I have. I don't see how to make it happen. I took the components that were here and shifted them up. That's these components. That's the Schottky diode protecting backfeeding the retro system. Those are 2 capacitors and a resistor, I think, for the crystal, which is here. So I've shifted those up, and then I've taken these address lines and I've routed them to the pins that they go to. And you can see I've gone up and around where possible. That's to give me more space available in this area of the circuit board, so that I can take these lines out and pull them up and veer them sort of in this location and give me room to get traces around. It's not going to be a panacea, because to take a trace up and around, you still need some width. You need essentially the trace width and times 2, because you need a gap between it and the next trace. So it ends up each trace takes twice the trace width. I may have to get rid of this bypass cap. This is on the 3.3 volt rail. That's probably okay, because I've got another 3.3 volt here with a bypass cap. That's within a few millimeters. And I've got another one down here, another one down here. I've got lots of 3.3 volt bypass caps. I think losing one wouldn't be the end of the world. That may then allow me to take these data line vias and just sort of smear them up against the edge of the chip. I'm still a little bit concerned about getting CE and A10 both through this gap here. A10, probably viable if I can take these vias and shift them over enough to the left. Remember, I can't shift them too much to the left because it stops the pins, the other traces coming out from the other pins of the RP2350. I'll also have to move these vias over a little bit so I can get CE through a gap here, and the trace won't be that wide. So I'm not out of the woods here, but I'm starting to think that I might be able to get this done. The other thing I've got a little bit of leeway on is the flash chip down here. I don't have a lot of room here. That's the number of traces that have to fit in this location. But maybe I can drop the flash chip down and move all the USB componentry over a little bit. I won't have my LED in the middle of the board, which will make me very, very sad. But not as sad as not laying out the board. So maybe move all those components over, move the flash chip down, leaves longer traces from the RP2350 to the flash chip. But who cares? We're only talking a few millimeters. And then maybe I can take these vias and smear them downwards and to the left here, and then this bypass cap, comes over this direction. So that might be what it takes to get this board laid out. I might have to rearrange all of this area of the board, shifting everything over as much as possible, as well as having moving these components up out of the way, and maybe getting rid of this bypass gap. And then I can take all these vias and squish them left against the chip as much as I can, sort of run them out straight. And then I might have enough width to get my traces through. I think if it's viable, I think that's the way to do it. I'm still getting hung up about this status LED. I know I shouldn't. I know it's silly. But I really wanted it in the middle. So I'm very sad now. It's the next morning, and I've had a bit of time to muse on my predicament. I haven't really reached any different conclusions. The reason why I'm in this mess is because I've moved the pins down by 2. Essentially, a pin that used to be here is now here, and all the way shifted down here. And that means that it's really hard now to get these traces from here back round this bypass cap up to here. I could possibly shift all of the pins back up by 1 pin. That would bring this USB connector back up in this direction. It might be possible to still fit all these components and traces in, having done that. My gut feeling is it is possible, although it'd be pretty tight. And I don't want to do that. I want to avoid doing that if at all possible. It would also end up looking a bit asymmetric, I think. In that it'd be really, really constrained down here. All the components would be packed together. And the components up here would be much freer. And that's a secondary consideration. So it's not going to, colour my thinking too much. But the option I'm planning to go ahead with this morning is move these components left over here. Squeeze everything in over here. And then probably rotate this flash chip by 90 degrees so it sits here. And then these components can all come down. And then these traces and vias can sort of flatten against the side of the chip and come down a bit. Similarly, I've already got space up here that I made last night to take a bunch of these traces and vias and stick them up here. And then see if that gives me enough capacity to get the 2 traces that I need to. Just to squeeze them round these vias and this bypass cap on both the top and bottom side of the board. But I'm going to take quite an unusual step for me before doing that. I'm going to back up the design as it is, so it makes it easier if I decide that is not the right approach to come back to this point in time, because it's going to take me, I think, quite a bit of time to move all these components down here, and I very much doubt that KiCad's undo functionality is going to let me just magically go backwards from there. So that's the plan. I'm going to save this off as it is. I'm going to move all these components over here. Then I'm going to try and squeeze all these traces and vias this direction, flat against the chip and extending above the top and down the bottom, and then see if I can get the traces through there. That's the plan. Watch this space. So I've shuffled everything around now. All of these resistors have been put in a line with the LED on the left hand side of the board. The inductor there stayed in the same position, but this electrostatic discharge diode pack has shifted all the way over from here to here, and the V-bus Schottky diode that stops backfeeding the USB host has shifted from about here over to here. But a big change really is that the flash chip, which used to be here on the board, has now I've rotated it and I've shifted it over left, and I've also taken a bypass cap that feeds that pin there on the RP2350 down to here. So it's a bit further away than I would ideally like from the chip, but not a particularly high power application, so I'm expecting it's going to be okay. That's given me all of this real estate on the top of the board to route to, so I can now pull these traces, like this pin here, I can pull the trace out and bring it straight down here and drop it through the board here, and I can do the same for these other vias, and that just gives me a bit of extra space to then be routing in this area on the board. A bit of an interlude. I've actually been holding something back, which is that right now I'm using minimum trace size of 6 mils, 6/1000ths of an inch. That's about 0.15 of a millimeter, and 6 mil gaps between the traces. That's the minimum that I'm prepared to go down to. JLC will actually fab down to 4 mil trace width and 4 mil gaps. I think they'll do this on their cheapest assembly service as well, it's the cheapest fabrication service. I've never gone below 6 and 6, and I don't particularly want to go below 6 and 6 because I worry about pushing JLC to the absolute limits of what they can achieve. One of the reasons for that is because I'm hitting problems getting the RP2350 boards fabbed anyway. I think they're pushing things there and they're not always able to properly fab the RP2350. I don't want to compound my problems by having weird problems because some of my boards have been misetched as a result of using really, really thin trace widths. But it is something that I am keeping in my back pocket. I am aware of that if push comes to shove and there's really no other way of getting this board routed, I can drop down to 5.5 or even 4.4 and then get it done. So I've made a lot of space down here. Now I've done a few things. I've moved these traces and vias further down. I've also rotated this bypass cap for the 1.1 volt nominal line, rotated it by 45 degrees. Now I might even sort of bring it down here and put it parallel with the edge of the board here, but we'll see. But as it is, it provides plenty of room for the traces from this pin and this pin to get up past the bypass cap and get past these vias. I'm nearly there. See, I've got these vias that were here pushed out up here, and this bypass cap has moved up a little bit, and I've squeezed these data line vias in. You may be able to see it better in this diagram. So that cap has moved this way and this way, and these vias have all tucked in here. I've even got the CS3 A14 line connected on the top side of the board up to here. All these address lines are currently connected. A10 is connected on the underside of the board, running down here and then back over here. So now all I've got to do is connect CE and OE, and then there's a few other bits and pieces like sort out these pads on the underside of the board. Now CE and OE are going to be a bit problematic given where I've broken them out. CE is above OE, but it's down below it here. So either I can move the vias around, move CE down to here and accept this bypass cap is going to push out a little bit more. Or I think I can swap those over, because if we go and look at the schematic, what's important is all the data lines are together, all the chip select lines are together, and all the address lines are together. Now, there's an added complication that the CS line 3 is in some circumstances A14. In fact, CS3 is only used on the 23128. So in that circumstance, it must be next to CE and OE, which will be CS1 and CS2 for that chip. But in all other cases, or at least for larger chip sizes, for 27 and 23256 and the 512, A14 needs to be next to all the other address lines. So it's important that that one is the one that is that chip select pin is next to all the address lines. But CE and OE don't matter. There are some circumstances where all three chip select lines will be used. They're all together. There are most of the circumstances where CE and OE are used together. Well, they're together, so that's fine. And there's one case, the 27 to 512, where there's only, I think, a CE line and not an OE line. It doesn't matter where the CE line is. If there's only one chip select line, well, it needs to be contiguous with itself. It doesn't need to be contiguous with anything else. So I can move CE and OE around like that. But if I do that, then actually routing this board will become even easier. As I say, I could have moved those vias around, but I don't need to move those vias around now because they're in the right locations. So I should be able to just get CE to come down. That's going to be tight there, but I think it's going to make it to there. Just tuck it in. Actually, I'm not sure it's going to make it. Go on, you can get through that gap. Go on. Oh, you're only a small trace. Well, that's annoying, isn't it? I mean, I still have other options, right? I can take the OE out on the top side of the board and drop it through there. And now it's done. I don't like that as a solution, but the board is now, I think, entirely routed. So from here on in, everything else is just gravy. What follows now is probably about half a day, maybe longer, of making things better. Both moving bypass capacitors as close as possible to the pins that they're supporting, making sure trace widths, particularly for the power lines, are as long as they possibly can, making sure traces for high-speed signaling, particularly the flash chip, is as short as it can be, make sure that the VREF support circuitry is as good as it can be, and make the board as aesthetically pleasing as I possibly can. At this point, it's worth me just stopping and taking stock and figuring out what the most important requirements are from here. And you can see that my boot and ground pads are not yet placed. The RP2350, when it's unprogrammed, so when they arrive, these boards arrive from me from JLC, I'll plug them in via USB, and assuming the layout is fine, they're just going to directly enter boot cell mode and I can program them. And from then on, the firmware that I program will be running a USB stack on the device when I plug it into USB. So I shouldn't need to be able to force the device into boot cell mode by pulling the boot pin down to ground. But I might. If a device gets bricked, then this will need to be used. The larger the pads are, and actually really importantly, the larger a hole I can put in the middle of the pad, the better for jumping the boards. With the ICE USB boards, those arrive when the chips are unprogrammed and they don't boot into the STM32's DFU mode. You have to actively force them in by pulling boot 0 high when you plug them in. I can't remember what pitch the pads are on, whether it's 1mm or 2mm, but it gives me the hole that I get in the center of the pad to allow myself to jam some pins in or some tweezers in or something is just a little bit small, but there's not a great deal I can do about that because the layout is so tight. Here, similarly, the layout is going to be fairly tight, but if possible, I would like to get holes in the center of these pads because it does make it easier to jump them. I find that the hassle coating on these boards needs to be, you need to cut through it with some quite sharp pins, and therefore having holes instead of pads is definitely beneficial. So that's actually the number one thing on my mind about improving the circuit board now. Another thing I've got in my head is the fact that these pins here, these 4 pins, are now unused because I only have 2 image select jumpers on this board. In fact, while we're talking about it, I'll just get rid of these silk screens for pins C and D because they're not going to be required. So that's going to give me a bunch of space up here. I don't really know what I'm going to do with that yet, but I did talk earlier in the video about maybe breaking out the SWD lines up here. So that's another thing I've got in my head. Now, coming back to boot and ground, this is where boot is currently broken out into a via. And I don't have room here for a larger via than this, unless I do something like take these traces all the way around the outside of it. That would give me space for a larger via. And the via is what I'm going to use as the hole in the center of the pad, most likely. But I have another option. On the top side of this board, I actually have some space here, which is just above the USB-C connector. I'll show you on the actual physical layout. It's this area here on the board, which is clear. And right now I've dropped a via through it so it gets a ground pour. But I don't need ground there for anything. So what I could do is I could take boot and ground and stick them here, put vias in the center of them and route boot on the underside of the board all the way over to the pad. So that I'm quite tempted to do that. And then the SWD and the SWD pins, I've currently got Schottky there and Swidio there. And when I talked earlier about this, I noted that it's going to be a bit of a challenge to actually route these up to these pins because I've got this big fat 5-volt trace here. And it really does need to come over here because that's where the voltage regulator is that steps down to 3.3 volts to power the RP2350. But what I might be able to do is maybe I can shift these cell pins to the right a bit and then via this 5-volt trace maybe here and take it the rest of the way on the top side of the board over to the voltage regulator, you know, bring it down into here. Because again, there's nothing, I won't cut off anything here. There's no functional ground here. So that would allow me to get the Swidio line up this way. Schottky's not in a massively good place, is it? But maybe I can take these 2 cell traces round the right hand side of Schottky. Now I can't do that immediately because there's not enough room for 2 traces there. That'll fit 1 trace. But maybe I can shift Schottky up a bit and to the left, and then I can get 2 traces round. So as I say, I'll bring these traces round here, and then Schottky can come up left of these cell pin vias, and they'll be able to get to this location on the board. And having debug pins, or at least footprints for debug pins on the board so they can be located on the top side of the board, it's actually really, really interesting from a debug perspective. And I suspect I want to do lots of debugging on the 28-pin ROM because I've got a whole bunch of different ROM sizes to implement support for. So I'm quite excited about what the possibilities are now for these extra pins. I've got 4 pins. For SWD I need 3. I need clock, DIO, and I need ground located there. Now actually I could do without ground because these pins here are ground to be jumpered for cell A and cell B. If I'm not using those, if I'm in debug mode and I'm not using those, well, these are spare grounds. What else might be interesting? 3.3 volts and 5 volts are always interesting to break out so you can externally power the board. I don't feel that breaking out run onto a pin is particularly interesting and exciting. I've never used the run pin on any of my boards. It would be fantastic to bring boot 0 up here, but that's just not going to happen, he says. But I'm just going to double check. I mean, boot 0 is down here, so what would I do? In order to give me a hope of making that work, I'd have to get boot 0 to here. So this side of all of these traces. I don't immediately see how I'd do that. Maybe I could get rid of this 3.3 volt trace to the flash and bring 3.3 volts in from over here somewhere, right? I've got 3.3 volts over there. Yeah, maybe. Maybe I could do that. That's probably going to cut my ground plane on the underside of the board though if I do that. And then what am I going to do? Bring the trace up here. Yeah, I could bring this ground via over to here and that would give me room. So then I would bring it up this side of the board. So maybe I could get it to here fairly easily. Then I'm going to have to jump it across these traces, and these traces are on both sides of the board, so that's going to be a challenge. Now, I just threw this CS3 A14 line down on the board. There's almost certainly something better I can do about that. I mean, I could probably jiggle things around here and actually take it on the underside of the board around this way. I think I'm going to hold fire on committing to put boot all the way up to the top of the board. If I can, though, I will, because I think it would be great to have that broken out on a proper pin. But it's a long way to get that trace, so we'll see how I get on. Making progress, slowly but surely. I have cut down these image select jumpers to just the two, and these are now a programming header and a debug header. That actually means that in a 28-pin Fire board, I won't need to have USB and Pro variants. There'll be a single variant, this variant, that provides both the SWD programming and advanced SWD features, but also USB in a single package. So that's nice. In terms of how I achieved that, I moved this Schottky diode to the right here, and that gave me a bit of room to get 3.3 volts coming over from this direction of the board and feeding in to the flash chip. I added a decoupling capacitor for the flash chip. It didn't have one on any previous revision, so I've added that in now because there's quite a long run for 3.3 volts to actually get to the flash chip, so I wanted some local storage of charge. The boot resistor here then feeds a trace that comes all the way up the board on both sides. I mean, it's got a long meandering route, and then it eventually makes its way up to one of the programming pins. See, my other programming pins are the two SWD pins and the run pin. I decided to give run a pin rather than have a test pad, just for consistency with everything else. And obviously you need a ground for using SWD, but there's a couple of grounds exposed here, as I said before, so that's fine. The only test pad I now have on the board is a 3.3 volt. It may be useful at some points to be able to inject 3.3 volts into the board to power it directly rather than going via the voltage regulator. I would quite like to expose another pin up here, which is 3.3 volts. So that would be up here on the board. But realistically, I don't see a way of achieving that. I could take it up here and around the outside and around here. That would mean breaking up the ground on the underside. Maybe that's not a disaster because I've got a consistent ground on the top side of the board here. That's all nicely connected. Actually, maybe that's something that I can get away with. I think I'll do that and have a look at it, see how I think that ends up. Because it would be nice, as I say, to have the ability to power this directly from 3.3 volts. I can't fit 2 pins in here because I have a run resistor that lives up on this side of the board. It's theoretically possible. I might be able to take this resistor and put it somewhere else and give me an extra 2 pins, but I just feel like that's going above and beyond what's necessary. Other things I want to do, I haven't run a design rules check yet, so I need to do that, see if I've actually got any unconnected traces and any traces that are too close to each other. So that's probably the next thing I should do, actually, run the design rules check. The design rules check has highlighted one unconnected trace, and this is the ground from the decoupling capacitor that lives down by the flash chip. There's no path through to this ground plane, so that's easily rectifiable. I can just move this boot trace a little bit like that, and then the ground should flow into it. Now the ground gets there, it's not automatically connected, so I'll need to whack a trace in there. So if I rerun it, that should now be fixed. So that's the unconnected traces, and then I've got a few other violations I need to go and sort out. I think it's basically done. I've got the 3.3 volt pad or pin here now. Put the components back. Everything looks nice and neatly arranged. On the underside, we have the programming pins labelled, and we have the 2 image select jumpers here. Managed to squeeze the silk screen in, plus a silk screen rectangle that allows you to write with a fine tip Sharpie or something what this ROM is. So all in all, I think this board is ready to send to fab. For reference, this probably took me about the same amount of time as it did to lay out the previous Fire board, the 24-pin USB board. That took about 8 hours. This has taken about 8 hours in total as well. A bit more than I expected it to take. I hadn't expected it to be quite so challenging to route the extra traces required for the additional pins on this ROM. Part of the issue here was that the chip select lines, those three chip select lines, had to be kept contiguous, and they also had to retain contiguity between the existing data pins and existing address pins. So I had to put the chip select pins in the center, and I didn't really have much of a say about that, and that really restricted the routing that I could do. But also just having to get more traces from here on the chip down to down here, going past the bypass cap that was here, meant it was all a bit more challenging as well, and that meant relaying out the flash section and this crystal support section. So hopefully next time you get to see this, I'll have one in the flesh, and we can get a high performance 28-pin ROM working. I have previously got a prototype of an ICE 28-pin ROM lying around here somewhere, which is functional, but there's some layout issues that mean that to support all the different ROM sizes required is going to require a new layout of that. Right now, Fire and the RP2350 is in pole position for a 28-pin ROM because it's much more performant. Now I've got the autonomous PIO DMA algorithm rather than a CPU algorithm, and the 28-pin ROMs tend to come in much faster access times, so that speed is going to come in very useful. So it'll be really interesting to see how well this performs. I was just doing some final checks of the schematic before sending to fab, and look at this. D- tied together, connected to D+. D+ connected together, connected to D-. Now, I don't know if you saw this earlier on in this video and were desperately screaming at the camera, but I'm glad I caught this, even though there is a way of programming the Raspberry Pi to switch around its D positive and D negative. That would be exceedingly tedious to have to do, so I need to go and fix this in the schematic here, and I also need to fix it in my layout. Now I'm going to have to change the pin assignment in my schematic because this pin here does need to connect to D+, so I'm going to need to do a switcheroo on both sides of the anti-static diodes. Fixed it. I had to rotate this ESD package around by 90 degrees in order to be able to get the traces to route from the USB-C connector itself. I think we're now good. I've double checked the schematic, happy with everything else, so I'm now going to send this to fab. This PCB is the gift that keeps on giving. I've just gone to JLC to order this board, and the Schottky diodes that I've used on the board are not available. They've got 13, and they require 20 to assemble 5 boards. Now there's only 2 on each board, but I guess they waste some parts putting it into the pick and place machine. So the reason I used this part in the first place, which is a fairly unusual part, it's a very small Schottky diode, is because I was very constrained for space on the 24-pin boards. You can see that here actually I've got, well, it looks like plenty of space. There's a little bit of extra space. I mean, that's probably 0.5 millimeter there, so it's not as much space as it looks. But I can almost certainly fit larger Schottky diodes on this board. That was one. This is the other Schottky diode. Again, I think I can probably fit a bigger part on here and it won't cause me too many problems with the layout. So that's what I'm going to do with this board. It's going to take me a bit of extra time, but actually I'll end up in a better position, assuming I choose the correct part, because the larger parts tend to be cheaper than this really small part, and obviously the availability should be better. So I've chosen to replace the MSK 4005 Schottky diode with an IN 5819WS. This is on JLC's basic parts list, unlike the MSK 4005, so this will be cheaper, 60 cents cheaper per board because I'm making 5 boards. And it copes with 25 amp inrush current, and it has a forward drop of 600 millivolts. So 5 volts will drop down to 4.4 volts. The dropout voltage of the AP2112 voltage regulator is about, I think it's 250 millivolts. So I've got loads of spare capacity in here. 4.4 volts is going to be plenty to drive the voltage regulator that I'm using. So this is a good part, and the fact it's cheaper is just a bonus. This new diode is the courtyard of the standard footprint in KiCad, is overlapping with the courtyard for the flash chip. I'm comfortable that that's going to be just fine. If we look at, this is a, I've checked the dimensions of the diode, and it's way, there's huge amounts of clearance from the flash chip, so that'll be just fine. And again, up here we've got plenty of room for the other diode up here. It's possible that I can actually squeeze one of these diodes into the other fireboards if I make the courtyard much smaller and maybe do away with most of the silk screen. I'll have to explore that, because I don't want to be beholden to parts that JLC have no availability of. I mean, if they've got 13 on their website, it wasn't a great choice to begin with, but I didn't have a huge amount of choice, I thought, because I was trying to squeeze something so small into the space. So I'm going through the ordering process now. I'm just uploading the redone Gerber files. Okay, those have been uploaded. Let's make them red, because this is a fireboard after all. I shouldn't need to change anything else here. I just want to double check, remove the mark they place on the PCB is set. That's now appears to be the default. I'll enable PCB assembly on the top side. That goes down to a build time of the PCBs for 24 hours. So that all looks good. I don't need any advanced settings. So I move on to next, and it will allow me to upload the BOM file and the position file. Process that. Now we should get one error here. This error at the top here. There are a bunch of capacitors of the same value and the same part number that use a different footprint type. Now, what JLC is trying to do here is suggest maybe I copied and pasted something and I didn't change the part number of one of the two capacitors. So I took an existing capacitor and I copied it and used it somewhere else, and I gave it a different, and I expected to give it a different value and a different part number, but I forgot to do that. That's all fine. I'm using a different footprint here because that's required for laying out the RP2350 voltage regulator circuit, the V-core circuit. So that's expected. So I'll just tick those items, and then JLC will populate those parts. I'm just going to quickly scan down this and look at the parts that I've changed. Just double check everything else. The most expensive part is the RP2350, followed by the flash. Then probably the crystal is the next most expensive, and then probably the weird polarized inductor that the RP2350 requires, and then the USB-C connector. Yeah, so this all looks good to me. The quantities, I've not gone through and double checked all the quantities. Just do that for the resistors. Yeah, 10 of those, 10 of those. Yeah, that all looks good. So we'll go on to the next page, and we'll actually look at the component positioning now. So this is not just where in the X and Y coordinates the components are on the board, but also their rotation, because KiCad and JLC quite often have a different view of the rotation of components than each other. So it's drawn my board, and now it's drawn on all the components. And you can see on my silk screen a pin 1 marking. So the oscillator, pin 1 is where these two lines join, and JLC put a pink dot on the component showing you where pin 1 of that component will end up. So that's correct. Here, this component has a longer line, pin 1, and a pink dot. They line up. The negative of a diode is where the, I don't know, scoopy bit ends up. So that's correct. The RP2350 is correct. That's pin 1 there. Flash is correct. Polarized inductor is correct. ESD diode is correct. Negative of that is correct. Negative of that is correct. So this all looks good. I'm also checking that every single component has a component on it, and that I've not accidentally not placed some components. So they all look correct. And now I also want to look at the position of the USB-C connector. So those pads look pretty good compared to the pins, and the legs are in the center of the holes from that dimension. We'll also take a look underneath, and we can see that it's in the center of the holes in this dimension. This looks right. I'm just doing a final double check and looking that every component type is what I expect the component type to be. That's a resistor, that's for the run resistor. There's capacitors for the voltage regulator, some decoupling caps, more decoupling caps, caps and a resistor for the oscillator. That's one of the Schottky diodes, bypass, lots of bypass caps, inductor, flash, various components there, diode, ESD diodes, another diode, a bunch of resistors. All looks good. I mean, worst comes to the worst, most of these components I can hand solder. I have stock of these components. I can hand solder them. So if I've screwed something up with actually positioning of the component or the part number of the component, it is something that I can fix later. So JLC want $48.64 plus tax plus shipping for these 5 boards. Quite expensive because there's just 5 boards being manufactured here. You can see the largest charge actually is the extended components fee. I've got 7 extended components on this board, clearly. All of the RP specific components are extended ones, but actually this is cheaper than the last board, so I got fabbed Raspberry Pi boards because those had the extended component Schottky diode, which I don't have anymore. I hope you found that video interesting and useful. I did the layout that you've just seen on Thursday last week. That was Thanksgiving, and it's Tuesday today. Yesterday, JLC notified me that my 28-pin versions of One ROM have shipped, so hopefully we'll see them in the flesh next week. Till then, rock on.